Sorry, it took me a while to get that turned on for you. When I go back and watch these, sometimes I'm more like, but I always think I'm like Marlon Brando or something. He never watched a movie, don't even know who he was. Anyway, one of the worst Al Pacino movies ever made, Scarface, is like this huge. Isn't there a whole like video game on him? Anyway, all right. So we did the elevators. We looked at forces. Today we're going to look at friction, tension, and things in equilibrium. All right. When things are in equilibrium, they're going at a constant velocity, or they're not moving. Okay. That's when when all the forces are cancel out, then the thing is in equilibrium. And if I give you an equilibrium problem on the exam, it will test you on your knowledge of vectors and how to apply them and how to add up forces and all that. And then you'd find the missing force or something like that. It's very similar. An equilibrium problem, remember the beach balls with the fire hose blowing? That was an equilibrium problem. You just didn't know that's what you were doing. So without further ado, let's get started with friction. Friction. And we're going to start off. Um, this is a Tina Turner lecture because we're going to start off nice and easy, but then we're going to end a little bit rough. Okay, as we talk about the frictional forces. All right, so here we go. I didn't call up your slides, but what I wanted you to look at is what's inside an atom. This is what causes a frictional force. All right, all the forces. All right, the fundamental forces. Hold on, let me call up your slides. Let's do this. As they say in the who's that, Home Depot or Lowe's? Somebody says, "Let's do this." And I'm wasting your time. Bouncy, bouncy, bouncy. Come on. Son of a bitch. All right, come on. Sorry. It's like, give me a break, dog. Okay. Anywhere up here? Yes, here it is. Before we get too far into this, let's go ahead and call this up real fast. All right, Newton's second law. We looked at Newton's third law, free body diagrams. We did that in class. Here it is broken down into vectors. Newton's third law, we looked at that problem. Here's where we stop. Fundamental forces. All right, here are the three fundamental. In nature, there are two general types of force, fundamental and non-fundamental. All right, the gravitational force that two massive objects attract each other or attract things to it. The strong nuclear force, if you think about it, like charges attract or repel each other, opposite charges attract. So how the heck do I get 74 gold? What's the atomic number for gold? Hell, I wish I had. I need to get a freaking whatever the thing is, whatever the element is that requires 74 protons. All right. If you think about it, and they have this very strong force that repels them. What the heck ties them together? Well, it's the strong nuclear force, and the electroweak force is the force that builds the even smaller things in the atoms, like the neutrinos flying through your thumbnail right now. The sun is producing billions of neutrinos a second per square inch. And you can't see them because of the weak nuclear force. All right. Anyway, but we can catch them if we go way underground. So, but what causes? So, and if you think about it, now here's the cool thing. Here's something that's kind of cool. So this is all kind of an intro, and I've got to show my ugly mug. I'm sorry. So if you think about it, now think about this. There we go. Think about it. So what if the proton, little bitty proton, I'm talking about the fundamental forces, I'm going way off the deep end, none of this is testable, you can stop the video now, but I think this is pretty cool. Anyway, so if you think about it, the proton, if the proton is here at UMKC, then the electron circling, say UMKC is the nucleus of a hydrogen atom, then the changing energies and flitting around it could be as far away as like Odessa. All right, there. Most of the universe is made up of no space, nothing. You know, there's nothingness out there. As a matter of fact, the density of the universe. Now, this will blow your mind. The density of the universe has been calculated. We know this. The density of the universe is 4 hydrogen atoms per cubic meter. And if you want to know what a cubic meter is, that's about how much space is in a Prius. All right, that's the sitting room. That's the passenger area of a Prius is about a cubic meter, or the front seat is about a cubic meter, and 4 hydrogen atoms. That's it. So there's not a whole lot of stuff. So if there's that much space we're talking about between the atoms and electrons, why do we even have coffee breaks? Why does anything stick together? That's the strong nuclear force and the weak nuclear and the weak the electroweak forces working. But the electromagnetic forces, and the electromagnetic forces working. And so when I go walking, as this book says, this book is great, because it talks about and this all has a point, because I'm going to get to why. Yeah, here it is. Call it this. This is a cool little book. I bought this book at a little science store. What physics is all about. If it was up to me, I'd make you all buy this $14 book, and it would be our textbook, and I would just riff off it from there. You know, why is the sky blue? How did the universe begin? It's all those questions that kids ask that it's just wonderful. So look at this. Here's the nucleus, and here's all the. So stupid electrons? Why does it hurt when you bump it? Why can't I walk through things? Empty space, right here. Okay, so why can't I walk through things? Mostly empty space. You might wonder why we can't walk through a lamppost and other things. While protons and electrons attract each other, 2 sets of electrons repel each other. So when the electrons on the edge of your forehead meet the electrons on the other way, and so here's the kids in there, bonk, stupid lamppost. Okay, and so there's the feel of the force. So we feel the force, all that kind of stuff. I'm going to stop here. This has just been a little intro to what we're getting ready to talk about. Oh, I might as well keep going, because ugly hand. All right, should be. All right, so we're talking about we're going to talk about like tension. Here it is. Okay, here it is. All right, so all the other forces that we're going to talk about, like friction, tension in a rope, normal or support forces, those are all examples of non-fundamental forces that come from the electromagnetic forces. All right. Okay. Or interacting with gravity. So only fundamental force. There's 3 fundamental forces: the electroweak force, or the electromagnet. There's the electric. I think I like to split it up into 2. Okay. So let's talk about friction. Let's talk friction. All right. Oh, well, he's talking gravitation here. I want to get to the normal force. I'll talk about gravitation a little bit later. Pushing down, weight going down, normal force going up, and we looked at the elevator problems and all that kind of stuff. There's the apparent weight. Now, here's friction. Surface, there is a force acted on the object. The component of this force that is parallel to the surface is called the frictional force. Okay? And these microscopic contact places, and it's also caused by electromagnetic forces and things. Friction opposes the movement. Static friction means there's no movement. If I pull on this, it's strong. If I pull, no movement. Pull as hard as I can, see the forces get each time, then I'm up to the, notice, reaction, action, and then the maximum is right when movement begins. All right, and here is the magnitude is F of S max, where F of the static frictional force is less than or equal to the maximum static frictional force, which we just saw in the previous slide. 0 is always less than the static coefficient. Oh, This is called the coefficient of. Note that the magnitude of the frictional force impact area of the surface. That's a good. That's a good concept. All right. Static friction opposes the impending relative motion. Kinetic friction opposes relative does occur. So if you're sliding on a sled, there's a coefficient of kinetic friction between you and the snow. All right, I'm going to stop here because this is going to be way too long.